Now that we have a decent idea of what functions in two variables look like, I want to talk about finding limits of functions in two variables. The importance of doing this is to be able to use calculus with my functions in two variables, because functions of two variables do a pretty good job of modeling the real world I live in. So now we need to figure out how the work we did before when we were working with calculus of a single variable can be adapted or modified to work with multivariable functions. I'm going to start by seeing what a limit might look like for a function of two variables. The limit of a function of two variables is defined as a function f of xy has a limit L as p of xy approaches a fixed point p naught of AB if the absolute value of f of xy minus L can be made arbitrarily small for all p in the domain of my function that are sufficiently close to the point p naught. This can be written as the limit as xy approaches AB of the function f of xy is equal to the limit as p approaches p naught of f of xy, which is equal to L. Now, we need to be really clear about what sufficiently close to means in the case of more than one variable. The point p of xy is considered sufficiently close to the point p sub naught of AB if the distance between the points given by the square root of the quantity x minus a squared plus the quantity y minus b squared is small for points p on all sides of p naught. In calculus of a single variable, I only had two sides of a point that I had to worry about. I could come from the left or I could come from the right, and the limit had to be the same. But in multivariable calculus, now I have multiple sides along a surface that I have to think about. So now I want to give you the formal definition of the limit of a function of two variables. A function f of xy has a limit L as p of xy approaches p naught of AB, which is written in limit notation as the limit as xy approaches AB of f of xy is equal to the limit as p approaches p naught of f of xy, which is equal to L, if given any epsilon greater than 0, there also exists a delta greater than 0, such that the distance between my function value and the limit L, written as the absolute value of f of xy minus L, is less than epsilon whenever xy is in the domain of f and 0 is less than the distance between p and p naught, which is given by the square root of the quantity x minus a squared plus y minus b squared, which has to be less than delta. So I want to revisit what sufficiently close really means here. When I say that the distance between p and p naught is equal to the square root of the quantity x minus a squared plus the quantity y minus b squared is less than delta, I mean that the distance between p and p naught is less than delta as p approaches p naught from all possible directions in my domain. The limit only exists if f of xy approaches the limit L as p approaches p naught from all possible paths in the domain of f. For the most part, if I'm given a function in two variables that is a really well-behaved function, such as a polynomial function, with no holes or gaps in the domain, then finding a limit of a function in two variables can usually be accomplished by direct substitution. However, we will encounter many problems where we have to actually look at multiple possible ways for my path to approach the point p naught. So now I want to define limits of constant and linear functions. I'm going to let a, b, and c be real numbers. The constant function f of xy is equal to c has the limit as xy approaches ab of c is equal to c. If I have a linear function, f of xy is equal to x, then the limit as xy approaches ab of x is a. So this is just the direct substitution of a for x. If I have another linear function, f of xy is equal to y, then the limit as xy approaches ab of y is equal to b. Again, direct substitution of b for y. Now let's look at the general limit laws for functions of two variables. I'm going to let capital L, capital M, little a, b, and c be real numbers, and I'm going to assume that the limit as xy approaches ab of f of xy is equal to L, and that the limit as xy approaches ab of g of xy is equal to capital M. I'm going to assume that little c is a constant and that m and n are integers. So my limit law for the sum of two functions is that the limit as xy approaches ab of the sum of f of xy plus g of xy will be equal to capital L plus capital M. In other words, the limit of the sum of two functions as xy approaches ab becomes the sum of the limit of the two functions. The difference of the two functions, the limit as xy approaches ab of f of xy minus g of xy, is just the difference of the two limits, capital L minus capital M. If I'm taking the limit of a constant multiple of a function, the limit as xy approaches ab of c times the function f of xy will be c times the limit of f of xy, which is equal to c times L. The product rule states that the limit as xy approaches ab of the function f of xy times the function g of xy will be equal to the product of the limits capital L times capital M. The quotient rule states that the limit as xy approaches ab of the quotient f of xy over g of xy will be equal to capital L over m, assuming m is not 0. In other words, the limit of the quotient of my two functions is the quotient of the limits, provided the denominator function has a limit that is not 0. My power rule says that the limit as xy approaches ab of the function f of xy raised to the n power will be given by the limit value L raised to the n power. And the m over n power, or rational power rule, states that if m and n have no common factors and n is not equal to 0, then the limit as xy approaches ab of the function f of xy raised to the m over n power will be given by the limit value L raised to the m over n power, where we assume that capital L is greater than 0 whenever n is even. So now let's work an example. I want to evaluate the limit as xy approaches 2 and negative 1 of the function xy to the 8th minus 3x squared y cubed. I'm going to use the limit law for the difference of two functions here, so that the limit as xy approaches 2, negative 1 of the function xy to the 8th minus 3x squared y cubed becomes the limit as xy approaches 2, negative 1 of xy to the 8th minus the limit as xy approaches 2, negative 1 of 3x squared y cubed. I can find these limits using direct substitution, and I get 2 plus 12, or 14. Now you get to try it. Pause the video and evaluate the limit as xy approaches e squared 4 of the natural log of the square root of x times y. When you're ready, restart the video to check your understanding. In this substitution, I notice that I have the natural log of xy to the 1/2 power. But don't let the power really get you bogged down. There's a much simpler way to approach this. I'm going to look at the limit as xy approaches e squared 4 of the natural log of the square root of xy. I'm going to make direct substitution. The natural log of the square root of 4e squared becomes the natural log of 2e. Now I can separate it and get 1 plus the natural log of 2. I could also have broken up the natural log of the square root of xy to be the natural log of the square root of x plus the natural log of the square root of y. But when I have a well-behaved function, It's just as easy to go ahead and use direct substitution like we just did. Be sure and let me know if you have any questions about working with these limit rules and finding limits of functions in two variables.